Uh, Hello, good morning, everyone. I want you to my lecture today. Of course, today we're starting a new chapter that we call clustering in machine learning. Okay, so the outline. I'm actually gonna walk us through how to differentiate between supervised and unsupervised learning. I'm actually going to do that and unsupervised learning. I'm actually going to do that so that you're going to have opportunity to know where clustering actually for. Then I'm going to introduce us to clustering, okay, with fundamental principles of that. I'm also going to talk about the types of clustering. Then I'm actually going to have a one-dimensional demonstration of that. Okay, so both of us gonna talk about in machine learning world um, and statistics in general. We can actually classify learning into two when it comes to learning from data. Okay, so when we want to talk about supervised learning, of course, that involve learning a function or you're mapping from input data or to output label. Okay, so that's why you can see you got an input X and actually mapping into an output label. Okay, so the goal of that is actually to look at the relationship that exists, between X and Y, okay, and so that we can actually explain or we also want to make a prediction, you know, um, the we got some supervised algorithms that under that, if we want to talk about the linear regression, the logistic regression, the support vector machines, neural network, and so on like that. Okay. So, if you, for linear regression, of course, require the output label has to be continuous in nature. And of course, when Y is kind of discrete or kind of categorical, we're going to go for logistical regression or neural network or support vector machine. So all of that, you know, the kind of analysis that we conducted when we have access to X and Y, why the outcome variable is actually present, as you can see. Okay, so that is for supervised learning. Now, at times we can have a situation where we don't have an output data Y. Okay, we only have X. Okay, so which is more or less like we are learning without a teacher in the sense that we don't really have an output label Y. Okay, so situation on where that occur, okay, that kind of learning can actually be categorized as unsupervised learning. Okay, so the model will work with data that doesn't have label output, and instead our intention is trying to find the hidden pattern or trying to understand the structure within data. Okay, so generally speaking, we are not interested in looking at the effect of a particular variable on another variable. Don't forget, we don't have an output variable that we also call an outcome variable Y. So the goal is just to focus only on X, and with the intention of trying to uncover what I call the underlying probability distributions or structures or relationship among the X only. Okay, so when you are doing that, I need you to pay attention to what I have here. So um, we more or less like, trying to, maybe we are classifying or we are grouping in a way. Okay. So depending on the characteristics of our interest that we actually want to figure out. Okay. So generally speaking, I'm actually gonna say the key difference that exists, between the supervised and the unsupervised learning. So I'm actually going to say the supervised learning requires, you having labeled data, okay, while unsupervised learning, you're working with unlabeled data. So unlabeled, say labeled and unlabeled, we're actually referring to the values of the outputs, okay. And when do we use supervised learning? Of course, you use supervised learning for prediction tasks, for classification, and why the unsupervised learning is actually used for pattern discovery and data exploration. Okay, so where does this actually fit? Whenever we are learning from, like I said, we live in a stochastic environment. We live in a probability space. Okay. We want to secure our environment. We want to understand our political environment. We want to understand our medical environment. We want to understand our environment in general. Okay. So we need knowledge to be able to understand that. And where would the knowledge come from? The knowledge is going to come from information that we got. Okay. Where would the information come from? The information is going to come from data. Okay, so which means we need to collect data. So everything is going to start from data. And the moment we have data, we don't have access to that knowledge and information. A lot of stuff has to be done to data. Okay, so because data are massive in nature, we uh, need to do some kind of cleaning. Okay, we do cleaning, we actually exploit. Okay, we know exploit the data. I remember what John Tukey said in 1970 when he was working on his paper called Data Exploratory Analysis. He said before specifying any model, okay, we need to first get to know our data set. You refer to that as doing what I call a detective work, okay, trying to get to know our data. So we're trying to be able to exploit the data, either numerically or graphically, okay? And of course, the domain knowledge is required, um, before we can actually, consider some features, okay? We got to believe that those features are connected, okay? And that is the reason why we are interested in them. So we do a lot of visualization, like I said, having a graphical representation or graphical summary of the data set, that actually fall under exploratory data analysis. And after we understand, their data, then we can now use a model. Don't forget, a model depicts reality. Okay, so depending on whether your intention is to explain or to predict. So if we will actually want to predict, of course, it's expected that you split your data into training and test, where you're going to learn the model from using the training set, and you're going to validate your model with using the test set, and you need to put into consideration, tensions that we discussed the other time, which include the bias and which included bias and variance, tension, and so on, like that. And don't also forget, we talk about, you consider when you are specifying your model, you need to consider a model that will not underfit and a model that will not overfit. We did all of that in this class. And of course, you do model validation because the only way you can trust your model is if a model actually perform for a great job, and of course, so we got a way we evaluate our model. Okay, so all of that, I think I will talk about them before. Now, I want to introduce us to clustering now. Okay, so in clustering is an unsupervised learning technique, because we don't have label, or there's no output variable. We only have input variable, okay, which could be one, could be more than one, and so on, like that. So I'm actually gonna say clustering is a type of unsupervised learning, where the goal here is to group a set of objects, okay, in such a way that the objects in the same group, okay, they are more similar, okay, to each other than those in the other group. Of course, I told you the other time, we live in an environment where there's variations. Because of that, we are not necessarily going to be in the same group. Okay, we're not necessarily going to be in the same group. So, which means if I have heterogeneous data, okay, the intention in clustering is actually um, to partition, is to partition them into homogeneous groups. Okay, so partition them into homogeneous group in such a way that within a particular group, they're all going to look similar, just like the way you guys are sitting right now. You're sitting in groups, and of course, um, we actually going to do the grouping in such a way that the intra class variation will be minimized. I know that we are not going to sit on the same spot, but the distance between uh, those who are sitting together will actually be minimized. Okay, so that is what we mean, um, you know, by clustering. Okay, now we got a lot of measures that we actually are going to use when it comes to this. So we call them the similarity measure. Okay, so we actually going to focus on what I call, distance. Okay, so we measure the distance between objects. We actually expect, that the distance should be actually minimized, for them to be classified or to be in the same group. So I'm going to be unfolding that as time goes on. Okay, so that is that. I remember what Austin Anatol, said. Said specifying an appropriate dissimilarity measure is far more important in obtaining success with clustering than choice of clustering algorithm. Let me say we got some kind of clustering algorithm, that we actually use depending on intention, depending on, the characteristics of interest. But there's something that is embedded, in in any clustering algorithm is the dissimilarity measure. So, and that's why we pay more attention to the similarity measure, okay, which I'm trying to echo RC et al. Okay, so we actually need, if we want to do the idea of clustering, we need what I'm actually called domain knowledge. The domain knowledge is actually essential for selecting the right features, interpreting results, and ensuring that the clusters generated are both meaningful and they are actionable. We don't just work on features. We got to make sure that the features, that we use, which I call the explanatory variables, they actually need to be connected in a way that they actually going to allow for meaningful interpretation. Okay, so the expert knowledge is actually needed. And of course, if you want to group, okay, objects, the expert knowledge is needed when it comes to how many groups do we actually want to have, okay, among other things. Okay, so and so on like that, like the approach to use the statistical or machine learning approach to use, okay, all of that requires expert knowledge, even choosing appropriate algorithm that we're going to use. Okay, all of that as actually depends on the expert's knowledge. Okay, so what is the goals of clustering? Okay, like I said, in clustering, all we're trying to do is to classify objects into groups in such a way that in each group, the objects are more similar. Okay, and our intention is, as you can see, what I'm trying to show you here, I got 3 clusters, right? This is in a circular shape. It could be in whatever shape, it doesn't really matter. So our intention is we actually want to minimize intra-cluster distances, between object classified that are in the same group. Okay, and we also want to maximize, which is synonymous with maximizing the inter-cluster distance. Okay, like the distance between this group and that group has to be significant, has to be maximized. But object in the same group, okay, uh, even though I know they are never going to sit in the same spot, but the distance they actually are going to have from each other is going to be minimized. So that is the idea, that is the goal of clustering. Okay, so I want to go into some examples of clustering right now. Okay, when there's something that we call document clustering. Okay, where we group similar documents in natural language processing. Okay, so you grouping related document when you browse. Okay, for instance, we browse for something, you actually gonna see a lot of stuff that will pop up, something that are related, okay, that are associated, related to that what you're trying to search. Not only that, if you go to a medical line, where we got different kind of genes expression. Okay, we want to group genes and proteins, that have similar functionality. Okay, so how can we actually group genes, proteins in the body with similar functionality? I want to believe when you look at the population of genes, they are heterogeneous in nature. So we may really want to have a way to cluster them. Okay, so that we're going to be able to say this group of genes, okay, this is the way they behave, and that group of genes, and that is the way they behave. And not only that, in financial, if you want to talk about in stock returns, we know there's a lot of price fluctuations, and when talking about price fluctuations, we're actually going to get some kind of stock, that whose they apply fluctuations look the same, look very close, and there are some that are really far from others. So we want to have a way to group stocks, with a similar price fluctuations, that will enable us to really understand, the financial data structure. Okay, so and in general, the idea is actually reducing the size of a large data set. Okay, when we do that, they're gonna be complicated as a whole. And the moment we actually provide some segments, like partitioning them, that's a way that more or less reducing the size of large data set. Okay, so there's a lot of examples when it comes to clusters. I also remember customers segmentation, like when you're trying to group your customer based on their purchasing behavior. My wife is into cosmetic products, and there are some customers that will call that she's gonna be so excited because she knows those customers. There are some set of customer that buys in high volume, and while some buys in low volume. So in a way, she has already like clustered them. So um so that is what we mean when I say customer segmentation. Also in image processing, like image or segmentation, where you want to partition a particular image into regions. You actually want to that we allow for what I call object detection. And not only that, you know, how it's also going to enable you to identify anomaly detection, and identify outliers or unusual pattern that are set. Okay, so I think the functions of clusters can not be application of that cannot be overemphasized. Okay, so I want to go into types of clustering now. When we talk about type of clustering, we got partitional clustering, we got the hierarchical. Okay, so and by partitioning clustering, okay, we're trying to like, can we have a way we divide the object into non-overlapping subset? So what we mean by non-overlapping subset is more or less that we actually believe that the object should be just in one category, in one cluster. We don't want situation where by it's going to be in one group and also going to be in another group. Okay, we don't want that. So we got some algorithm that we actually use when we're trying to partition, cluster like k-means, k-medoid, and so on like that. And we have hierarchical clustering. In hierarchical clustering, we actually believe some clusters are nested, okay, in another cluster, and with that we actually gonna use hierarchical tree. Okay, so they're gonna actually gonna have hierarchical tree. So we got some algorithms that actually handle that. So we got algorithm for partitional clustering. We got different kind of algorithm for hierarchical. Okay, so the hierarchical is useful when you want to exploit data, and particularly bioinformatics, it's very, very useful. Okay, I just want you to take note of that. So I'm actually, this is just to tell you we got two types of clustering, by partition or by actually produce what I call the hierarchical, by hierarchical tree. We're actually going to have an opportunity to see how some clusters are actually nested in another clusters. So let me just quickly put this. Yeah, when there are situations where that will requires the use of partitioning or clustering, and we got situations that will require the use of hierarchical. Okay, so for partitioning, when you have a good idea of how many clusters you need, okay, your data fit the assumptions of roughly spherical clusters, okay, or you are working with large data set, okay. The idea of partitioning, clustering is going to work. So in that situation, so you're going to think of using partitioning algorithm that we're going to talk about. There's so many of them. And what about when do we use hierarchical clustering? So when you want more flexibility, okay, because partitioning clustering is rigid, it's rigid to me. Okay, so when you want more flexibility in terms of the number of clusters, okay, and then when you need to handle complex cluster shapes or you want to exploit hierarchical relationship between data point, because at times the relationship could be hierarchical where some kind of clusters are nested in the bigger ones. Okay, so trying to showcase to you now how the way our partition and clustering look like. If I have this as original data set, okay, and of course I'm trying to say by partitioning clustering, of course we can produce two clusters based on this original data set, and based on this original data set, we believe that you know it's not going to make sense having more than one cluster, because maybe we feel that the distance is not that much, between objects. And of course, don't forget, like I said, in partitioning, clustering, um, you know, elements, object can only be in one cluster. Okay, only. Okay, there's nothing like overlapping. And when you talk about hierarchical, on the other hand, the hierarchical clustering, like I said, we could actually have, some clusters that actually have an hierarchical relationship with others. Like if you take a look at this guy now, P2 and P3, if you take a look at these 2 points, they are actually nested in P4. You see that? They're nested in P4 and all of that nested in P1. Okay, so this is it. If you want to start the hierarchical tree, you're gonna start with the smallest one, okay, which is P2, P3 now. So we're starting with that. So that have this, you can see P2 and P3, and of course the P2 and P3 nested in P4. So this guy now, so the P4 is actually so this, you can see this guy is bigger than this, right? So P2 and P3 nested in that, and all of that, all of this nested in P1, as you can see here. So this is the corresponding hierarchical structure for this. Okay, so when you take a look at this guy here, okay, P1 and P2, they are in a cluster, and P2 and P3, okay, and all of that nested in a big one, okay, in this, that is not mentioned. So here, that was why I say P1, P2, they're together, P2, P3, P4 together, and all of that nested in a bigger structure, as you can see. Okay, so the next is to talk about the type of input for clustering. Of course, if I want to do clustering, so I actually need input variables. Okay, the input variables, don't forget, like I'm actually gonna have the number of observations, okay, collected over variables. For instance, I may be working with maybe the crime variables, okay, crime variables and some states in the state in the United States, okay. So P is going to be the numbers of crime variables, okay, and N is going to be N, that is object now, is actually going to be states. So maybe what I actually want to do is to classify state according to putting into the putting into the crime variables. I actually want to partition states. That's exactly what I mean. Okay, so I'm actually trying to say here, um, there's going to be a matrix because I'm going to have n object against p variables, and of course, the p variables, the crime variable I talk about. Maybe I'm talking about theft, assault, homicide, burglary, drug offenses, and so on. Like that. That's what I'm talking about. Okay. Now, there's going to be a dissimilarity matrix that will be n by n, and that very n by n we talk about the object. Okay, we have information on how the similar the object are, the similar the states are. Now, I'm actually using the example of that. We can also construct a similarity matrix. So the takeaway is that the similarity and the similarity matrix are actually going to be a square matrix. Okay, just take a look at that, n by n. Now, I said something the other time, whatever measure you're actually going to use, whatever measure you're going to use, whatever algorithm you're going to use for your clustering, they actually have what I call the similarity measures. Okay. And if I want to talk about that, I'm actually going to talk about the distance between X and Y. Of course, the distance is non-negative because when object is classified, okay, we look at the distance from one object to the other. Now, if a particular object is in the same position with another object, of course, we know the distance is going to be 0. And of course, even if objects are grouped in the same group, okay, if they are in the same cluster, they're not going to occupy the same position. Okay, so we expect the distance to be greater than 0. So the lowest distance possible is 0. And that is only going to occur, when I'm actually referring to the same object. Okay, and of course, there's going to be a property of symmetry where the distance between X and Y is also going to be the same as the distance between Y and S. Okay, so we got some distance or metric. We talk about measuring, this dissimilarity measure, that need to satisfy triangles inequality. So the distance measure that we're using, because if I really want to know whether that particular distance measure is actually fantastic. It needs to satisfy triangle inequality. So the distance between X and Y should be less or equal to distance between X plus Z, plus the distance between Y and Z. Okay, so we we have some important measure of distance. We remember in this class we talk about the norm. Okay, the norm of talking about the norm of X minus Y. Now, okay, in Q space. Okay, we have this as the formula. Depending on what this is a generalized formula, this is a Minkowski distance. Okay, so where if Q equal to 1, that would be called Mantown distance. If Q equal to 2, that will be called Euclidean distance. Okay, so we can actually we apply this dissimilarity measure distance when we're clustering, and of course we can actually compare them whether they're gonna resolve to the same numbers of clusters. Okay, so these are the common distance measure that we use in clustering. Okay, I think I've talked about all of that. Talk about the dissimilarity measure. We also have similarity measure. The similarity measures is actually going to include the cosine, the correlation, and so on like that. But the most important one that we're actually going to talk about is the similarity measures. Okay, so I want to walk us through ways of clustering now. In the ways of clustering, we have the hard clustering, we got a soft clustering. And of course, what we mean by hard clustering is that just like, oh, we got a definitive assignment. We are a particular object can only be in one group. Okay, it can never be in the other group. If it is in this group, okay, it's exclusively a member of a particular group, is not going to be a member of another group. So, and that was why we call that mutually exclusive, because mutually exclusive actually means when this event occur, okay, that will prevent the occurrence of another event. So, which means the two object can a particular object cannot occupy more than one group. That's what we mean. And when that happen, the interpretation will be very, very simple, because of the fact that there is no probabilistic membership. This is very, very clear, right? That okay, particular objects can only occupy a particular group. So that will facilitate simple interpretation. So looking at the advantages for that, of course, it's going to be simple and efficient. Okay, very computationally less expensive, because there's what I call exclusive, there's a boundary, okay, between clusters, okay. Then because of that, it's like we're having a very clear assignment. Okay, there's nothing, because the data point can only be in one group. Okay, the limitation of that is that it's not flexible. Not flexible because we could have situation whereby um, an object can belong to a particular group and still belong to another group. So add clustering is not flexible because it emphasizes that you know uh, an object can only be in one group. Okay, then it's less adaptable to complex structure, because when you have complex structures, there's possibility that some particular object may be occupying more than one group. Okay, so soft clustering, on the other hand, because the fact that an object can be in more than one group, then there's actually going to be introduction of uncertainty. So, which means there's going to be probabilistic assignment. Okay, so object can belong to more than one group at a time. So now we can attach a probability, like what is the probability that okay, this object is going to be in group one, maybe 60%, why the probability that is going to be in group two, maybe 40%. So that's what we mean by probabilistic assignment. So which means we allow overlapping between clusters. So overlapping between clusters, because some object can be in one group, they can also be in another group. Okay, the advantages is of course flexibility, more realistic for some data, and limitations of that is number one is complexity. Complexity in the sense that probability is now being involved. Okay, because we have a probabilistic assignment of the probabilistic nature of membership, that will incorporate some kind of probability distribution into uh, the algorithm. Okay, so that is the complexity that we talk about. And of course, that will come with the higher computational cost. Okay, so at this point, we want to talk about some common algorithm for ART clustering. The first one is K-mean clustering. We have K-meter, we have hierarchical clustering, and we have a density-based spatial clustering of application with noise. So all of these, they are algorithms that we use for hard clustering. And don't forget what this algorithm, what hard clustering means. So actually means that you know object can only be in one cluster at a time. There's nothing like probabilistic assignment. Okay, we also have uh, common algorithm for soft clustering, like FOSSI C-means, Gaussian mixtures models. Okay, so these are algorithm for that. Okay, so I want to go into the type of algorithm now, for clustering, and I'm going to demonstrate, using an example for one dimensional. data. Okay, so gonna start with take a look at the picture now. Okay, here, this is partitioner. Okay, we partition into two. Okay, maybe here, this particular group may be workers in a company. Why this may be the same members of a family. Like I said, the domain knowledge and expert knowledge is needed. You know, when you are uh, partitioning. And of course, the hierarchical is trying to create, you know, a kind of an hierarchical tree, a decomposition of the set of objects, you know, where we believe that some object may actually be nested in another object. If you take a look at what I have here. So these are in one group, this is another, they're in another group. If you take a look at that, and they're all nested in this other guy here. Okay, so I think I'm gonna provide an explanation for that. Okay, so the whole thing is gonna start with matrix. Okay, imagine for instance I have 5 individuals, right? Okay, so I'm just trying to tell you how we construct this or how we partition that. So it's going to start with matrix. So let me just say the number that you see here is the distance between them. If you take a look at this guy and this guy, of course, the distance between itself is actually 0. Okay, so if you look at the diagonal here, it's just telling you the distance between me and me, the distance between me and me, that would be 0. Okay, now we don't consider here because of the agora or the value that you're going to have here is also what you're going to have here. So what is the point? So we're only going to focus on the upper triangular matrix. So we take a look at this guy now. Okay, so the highest is 8, the lowest is 1. You don't count 0. Don't forget, you know, the 0 is just the distance between me and me, the distance between the same person. Okay, so we're not interested in that. So what I mean here is that the distance between this guy and this guy is 1, as you can see. Okay, this guy 1 here, the distance between this guy and this guy. So, and the highest distance you can see here is the one between this guy and this guy is 8. So this is you know, the values here is already computed, is seen to be the distance between you know, between the two objects, any pairs object. Okay, so um I want to do this you know, on partitioning algorithm. One of the partitioning algorithm is actually k-means. Okay, k-means, you know, we're gonna talk more about this in class on Friday. You know, Friday we're gonna focus more on the algorithm one after the other, looking at the k-means, looking at the k-method, and so on like that. So, but you know what I want to do right now? For us, like I want to work for simplicity. You know, I want to see manually if I have one dimension objects, okay, and I actually want to group them into two. The object that I have is 1, 2, 5, 6, 7, okay, and I want to group them into two, okay. Now, what I'm going to do, I will randomly, with k-means, I will randomly select two numbers, okay. I will randomly select two numbers from the object, okay, and that will serve as my centroid. Okay, so let me say I selected 5 and 6. I'm just assuming. Okay, if I select 5 and 6, okay, now let's say we got this is the 5 here and this is the 6 here. Okay, now what we're gonna do, we're actually gonna assign the rest that are very close to 5, that are very close to 6. So 7 is very close to 6. I'm actually putting 7 here. And what is close to 5 here is 1 and 2. So if you take a look at this guy now, so that was how we got this. Okay. Now the next thing I'm going to do is to compute the mean of this guy and the mean of this guy. So the mean of this guy is actually maybe 2 point something, and the mean of this guy is 6.5. So now if I have that as the mean, so what I'm actually gonna do now, I need to rearrange. Okay, I actually need to be able to use the idea of the mean here to assign. So which means in the cluster, in this cluster here, I'm only going to assign numbers that are very close to the mean, very close to 2 point, let me see, when I say 8 divided by 3, so that precisely, okay, to 2.7. And the number very close to 2.7 is still 1 and 2, okay? Then here, what is the number close to 6.5 is still 6 and 7, okay? Still 5, 6, and 7, okay? You can see. So if you see the movement from here to here, okay, it doesn't really change anything. So we have 1, 2, 5, 6, 7. Now, if you want to continue to go again, let's say if you find the mean of this guy, that's 1.5, right? If you find the mean of this guy, that is 6. Now, can we what are the numbers that are very close to 1.5? You're actually gonna see it's still gonna be 1 and 2. What are the numbers close to 6? It's still this guy here. Okay, because of that, there's no change. And if there's no change, then we're going to say the algorithm converge. That's what we mean. And if you really want to know whether the intra distance, the distance between objects in the same cluster is minimized, we can actually, find the sum of square deviation from the mean. So we can do 1 minus 1.5. Okay, 1 minus 1.5, you squared is this guy. 2 minus 1.5, you square is this guy. 5 minus 6, 1, you square that. 6 minus 6, 0 squared. 7 minus 6, okay, that will give you 2.5. The 2.5 here is actually going to be the sum of square distance, within a particular cluster. Why am I doing this? Situation where at times we have different initial point. Okay, when you have different maybe cluster like here, having 2 clusters, or you want to have 3 clusters, 4 clusters, and so on like that. We want to compare which of the cluster is more appropriate or optimal. We can compare this particular value. Okay, the smaller one is actually the best. Okay, so how do we demonstrate the hierarchical clustering using the same one-dimensional objects? I got 1, 2, 5, 6, 7, right? So the closest is 1 and 2, right? If you take a look at this, the closest is 1 and 2. So I got 1 and 2 here. And when you have 1 and 2 being the closest, I'm actually going to sketch that. Okay, so for 1 and 2, right? I'm gonna do that. Now, now that I have 1 and 2, now, okay, the next thing I'm gonna have is like I'm having 1 and 2 and 5, 6, and 7. So what does it mean for 1 and 2? 1 plus 2 is 3. 3 divided by 2, that is 1.5. So which means what I have at the moment is 1.5, which is the mean of 1 and 2, then 5, 6, 7, which is what you have here. Now, the next thing that we actually want to do is to look for the next closest. The next closest, we've already secured 1 and 2. So the next closest here is going to be 5, okay, and 6. Okay, you can see 5 and 6. Okay, now we're going to do the same thing again. We secure 1 and 2, we secure 5 and 6, we find the mean of 5 and 6 again. The mean of 1 and 2 is 1.5. The mean of 5.6, the mean of 5 and 6 is 5.5. And don't forget, when you choose 5 and 6, we are left with 7. So we're bringing the 7 down. Now, when you take a look at what I have here, okay, what is close? The 2 closest number here is 5.5 and 7. So which means, don't forget, the 1.5, the average 1 and 2 is on its own. Then 5.5 is the average of 5 and 6 on its own. Then it means, don't forget, 7 is also closer to that. And that is why we're going to say, okay, the 5 and 6 are going to be nested. Okay, they're going to be together with 7. So 1 and 2 is this guy. 5 and 6 is this guy. And together with the 7. So that's why you have that. Okay, so the last example that I'm actually going to showcase, in case you have a matrix and you want to generate an hierarchical tree. Okay, no, I have 1, 2, 3, 4, 5. okay, the same 1, 2, 3, 4, 5, the same 1, 2, 3, 4, 5, and I actually want to draw, um, you know, I actually want to draw a hierarchical tree for that. Okay, now in the diagonal is 0, 0, 0 because there is a distance between 1 and 1. The distance between the same objects is going to be 0, 0, 0. So 2 here, they're going to give you all this. They're going to give you the distance. Like they've measured the distance and they realize that the distance between 2 and 1 is 2. Okay, the distance between 3 and 1 is 6. The distance between 4 and 1 is 10. The distance between 5 and 1 is 9, and so on like that. So these are distances, that have already been computed. So this is a distance matrix, okay? Now, if you take a look at this right now, okay, take a look at this right now, okay, apart from this one, okay, this one is the smallest, which is the distance between 2 and 1 is the smallest. And that was why we're having this. Okay, that's why we're having this. Okay, that's why we first connect 1 and 2. Okay, now the next thing now, after connecting 1 and 2, so the next thing that we're gonna do is so since 1 and 2 is we've already secure that right now. So the next thing we want to do is the old matrix that we have has now been reduced. And that was the reason why I said something the other time, clustering is also a way to reduce the dimensionality in the data set. So now, right now, since we've grouped 1 and 2, okay, based on what you based on the fact that is the distance between one and 2 is the smallest here. We have already grouped that. Then the new matrix is now going to be 1 and 2, 3, 4, 5. I mean 1 and 2 together, 3, 4, 5. 1 and 2, 3, 4, 5. Okay. So what we now want to do right now is to get some values here using this. What are we going to do? Okay. Like I said, apart from this guy here, okay, which is the distance between this guy and that guy, between the same thing, we're going to focus on this. So what is he saying? The distance between 1, 2, and 3 is 3. Okay, so I need you to say something now. We need 1, 2, and 3, 1, 2, and 4, 1, 2, and 5. So take a look at this. 1, 2, and 3, we mean I need a minimum between D1, then 1 and 3, and 2 and 3. Okay, so you want to consider 1 and 3. 1 and 3 is 6. Can you see this guy? Okay, 1 and 3 from this old matrix is 6. And that was why you have this particular 6. Then 2 and 3. Okay, 2, okay, and 3. Okay, 2 and 3 is 3 from the old matrix. And that is why you have this guy here. So what is the minimum? The minimum is going to be 3. And where is that 3 is going to be? So that is why we have this guy here. Take a look at that. Okay, so you're going to do the same thing to 1, 2, and 4. You get a minimum. The 1, 2, and 5 get a minimum. Okay, and you'll be able to get this and this. Okay, now the only new thing that we got in the second matrix, I'm going to tell you. Okay, this one, okay, is the one here. Okay, but this guy here, of course, they came from the old matrix. Just wanted to see that. They came from the old matrix. Now, this is where we are at the moment. Okay. Now, based on where we are at the moment now, okay, we need to be able to identify, okay, apart from this, we need to identify the smallest now. The smallest is going to be this guy. Okay. The smallest is going to be that guy. Okay. Now, when you have that, the next thing now is we actually mean there's the first metric we started with. We move to this guy. Okay, so here now we want to move to another matrix. Okay, this is where we are now, right? And don't forget, and I said, um, apart from this, okay, this is the smallest, right? So which means apart from drawing 1 and 2 before, we are now going to draw 3. That was why we have this one. Can you see that? On 3. Because this 3 is the next in the order. That's why in the hierarchical structure. Now, from here now, we actually want to go to another matrix, and the way to go to another matrix right now, here we've secure 1 and 2, and at the same time secure 3, because 3 is the smallest. We're now going to have a new table. Okay, we're going to have a new table. We're going to have 1, 2, 3, 4, 5. Can you see now? 4, 5. Can you see now? The diagonal is going to be that, and where it will be 7, 5, 4 coming from. Okay, so you can see here 7, 5, 4. Okay, that's going to be coming here. Okay, so we can look at the distance now. 1, 2, 3. Okay, and the 1, 2, 1, 2, 3, and 4. The 1, 2, 3, and 5. Okay, how do I get 7? How do I cause 1, 2, 3, and 4? Okay, you're going to consider that. So 1, 2, 3, and 4 will mean consider 1, 2 against 4, and then 3 against 4. So what is the minimum distance? So if you want to consider 1, 2, 4. So here 1, 2, 4 is 9. That's why you have this guy. Okay, then 3, 4 is 7. Okay, so 3, 4 is 7. So that's why you have this. So what is the minimum? 7. You're gonna do the same thing here. You figure this out. So you're gonna have 7, 5. So you're actually gonna see the way the structure is gonna be. So now that was why we actually have the kind of structure that we are having now. So, initially we draw that of 3, right? Okay. Now the next one is 4 and 5. Okay. The four and 5 is because, if you take a look at this, here the minimum. What is the minimum, right? The minimum here is 7. The minimum here is 5. Then from there, okay, if we have consider 1, 2, 3, 4 and 5, and of course the minimum is actually 5. Then we draw the next one, then we draw that. So that was how with that that was how we have that. Okay, so on Friday I'm actually gonna walk you through the K-means algorithm for multivariate analysis, the K-method algorithm for multivariate analysis. So is there any question before I go today? Okay, so see you on Friday. Make sure you all stay safe and have a lovely day. Bye for now.